Now, the previous example was an illustration of conditional probability. And conditional probability, don't forget, is the probability that something occurs given that something else has already occurred. So for example, what is the probability that my second roll is doubles given that my first roll was doubles? But this example introduces us to Bayes' theorem. I'm just going to put it up right here. And Bayes' theorem is also conditional probability, but it is conditional probability that tends to work in reverse order. So we are going to use tree diagrams to help trace our steps to help determine these probabilities. So this example says 2 cards are dealt from a well-shuffled standard deck of 52 playing cards. What is the probability that the first card is a jack, given that the second card is a jack? So I'm just going to show what the event would be. So I'm just going to mark it as E. And how about if I say J for jack? So we want 2 jacks. However, what we're going to determine is we want to know what is the probability that the first card is a jack, given that the second card is a jack. In traditional probability, it was what is the probability that the second card is a jack, given that the first one was a jack. Here we're kind of going in reverse order. So again, we're going to make our tree diagram. And we start out with our action, and the action is we're going to be dealing cards. How about if I just say cards? So you're dealt a card, and it could be a jack, or you're dealt a card, and it's not a jack, and I'll just say jack complement. The probability of being dealt a jack, that's 4 out of 52. There's 4 jacks, 52 cards. The probability of being you dealt your first card, don't forget this column here represents the first card being dealt. That's 48 out of 52 of it not being a jack. Then we branch off to the second card. So here's our second card. This can be a jack or not a jack. If the first card is a jack, then the probability that the second card is a jack, that's going to be 3 out of 51. We have 1 less jack and, of course, 1 less card. Here, this is going to be 48 out of 51. If the first card is a jack, then the second card not being a jack, it's still 48, but we have 1 less card, so it's going to be 48 out of 51. So you have to be careful on your probabilities here. These are not independent events. These are not disjoint events. So the probability of one depends on the outcome of another. So here's a jack and not a jack. The first card is not a jack, and the second card is a jack. That's going to be 4 out of 51. Don't forget, we have 1 less card. The first card is not a jack, and the second card is not a jack. That's going to be 47 out of 51. You see that? Now that I have my tree diagram set up, what is the probability that the first card is a jack, given that the second card is a jack? Well, here's the second card. This column represents our second card. Here is a jack here, and here is a jack here. So what's the probability of this occurring? Well, we take our 4 out of 52, multiply that to our 3 out of 51. That's approximately 0.0045. But here's our second card is a jack. Again, don't forget, given that the second card is a jack, here's a jack here. What's the probability of this occurring? Well, that's 48 out of 52 times 4 out of 51. That's approximately equal to 0.0724. So then the probability of our second card being a jack can be this one, or it could be this one. And since I have an or, for or probabilities, we add them together, right? So I'm going to have 0.0045, or it could be 0.0724. But this is the one that we're concerned with. What is the probability that the first card is a jack, given that the second is a jack? Well, here's the probability that the second one is a jack. But we want to know, of that, the first one is a jack. Well, here it is here. Jack and jack. So then this is going to be divided by 0.0045. So this is 0.0045 over 0.0769, and this comes out to be approximately 5.85%. So what is the probability that the first card is a jack, given that the second one was a jack? 5.85%. So we're kind of working in reverse order. We know this. We want to be able to determine this. So for general probability, we have the probability of B occurring given that A has occurred. And we know that to be the probability of A and B occurring. Divide that by the probability of A occurring. So if I mark this as A, and I mark this as B, so the probability of A and B occurring, that's this right here. So that's going to be 4 out of 52 times 3 out of 51, which of course we know to be 0.0045. And then we divide that by the probability of A occurring. Well, that's this right here. That's the 4 out of 52. And then these two are going to cancel. So the probability of B occurring given that A has occurred, 3 out of 51. But Bayes' theorem says the probability of A occurring given that B has occurred. That's the probability of A and B occurring. But we divide out the probability of B occurring. So the probability of A and B occurring, here it is right here. Again, that's 4 out of 52 times 3 out of 51. Of course, we know that as 0.0045. Divide that by the probability of B occurring. Well, B occurs here, but it also occurs here. So we divide out the 0.0045, which is what we did, and the 0.0724, which is what we did. We just know it as 0.0769. But there we go.